The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
Alright, for number 3 we need to find an interval of convergence for that series. So when you see things that are raised to the nth power but not the entire function, plus you have fractions and things like that, the test you probably want to go to in that situation is the ratio test. In general, as long as a function is not easily integrable, the ratio test is probably your strongest test, and especially when you're finding intervals like this. So let's use the ratio test on this. Let me rewrite the series real quick. So we have n equals 2 to infinity. We have 2x minus 7 to the nth power over the n times the square root of ln n. So we have a lot of different things going on here. You definitely would not want to try the integral test here. Too much stuff going on. Or really any of your other tests. Comparison would be very difficult. Root test would maybe help you, but only the top is raised to an n, so that also might be pretty difficult. Ratio test is your go-to test here. So ratio test, we're looking at the ratio of the n plus 1th term over the nth term and its absolute value. So remember that you can always write this because most of the time you're doing ratio test, your series function is a fraction anyway. You're just going to write the n plus 1th and you're going to multiply it by the reciprocal of the n. So if we sub in n plus 1, we get 2x minus 7 to the n plus 1. We get n plus 1 square root of ln n plus 1. So we're going to multiply that by the reciprocal of the nth, so we just flip that and we get 2x minus 7 to the n. On the top we just get that n root ln n. So the ratio test, remember, says that if you take the limit as n goes to infinity of this product, if it's less than 1 it converges, greater than 1 diverges, if it's 1 you can't tell. So let's see what we can cancel here. We have 2x minus 7 to the n plus 1, 2x minus 7 to the n. So this cancels out and we're just left with a 2x minus 7 on the top. N and n plus 1, ln n plus 1, and ln n do not cancel at all. So we're going to have to do a bunch of things with limits here. So, let's evaluate some of these things. So we have 2x minus 7. So what I'm going to do is, with the remainder, I'm going to group them in kind of logical ways. So we have 2x minus 7 times n over n plus 1. And then since we have a square root of this on the top and bottom, you can write that all under one root. And we have ln n over ln n plus 1. So remember that we're doing the limit as n goes to infinity of that entire product. So again, what I did was just rewrote everything here and I grouped everything together. So if this converges, which is what we're trying to find, where does this converge? This has to be less than 1. So let's see what goes on with these n terms, and then we can solve for x. Well, the limit as n goes to infinity of n over n plus 1, that's just going to be 1, because, again, you can think of it as a rational function, n on top, n on the bottom, same degree. Look at the coefficients. So as the n goes to infinity, this is 1, so you're multiplying by 1, that doesn't matter. By the same token, if this is equal to 1 as n goes to infinity, that means n plus 1 and n are the same as n goes to infinity. So you're doing ln of one of them over ln of the other. If those things are the same, then the ln's of them are the same, and that fraction is also 1. So all we have now is 2x minus 7, and if we want that to converge by ratio test, it has to be less than 1. Sorry, absolute value of it has to be less than 1. ratio test here is absolute value. So now we just have an absolute value inequality to solve. Remember that this can be written as is in between -1 and 1. So now we just solve for x, add 7 to both sides, we get 2x is in between 6 and 8, and divide by 2. You get that x is in between 3 and 4. Written as your interval of convergence is right there. So any x between 3 and 4 will converge. So the last thing we need to check here is what's happening at the boundary points themselves. We need to check what's happening at 3 and at 4. Okay, let's take a look at 4 first. If x is 4, then that top part of our series, which I just erased, is going to be 1. So if x equals 4, the top of our series is just 1, so now our series looks like this. N equals 2 to infinity. We're going to have 1 over n square root ln n. So this series we need to evaluate, does this converge or diverge? So to evaluate this series where we have 1 over ln square root ln of n, we're going to have to use a comparison and then an integral test. So what we need to do here is compare and say that 1 over n square root of ln n is always going to be greater than 1 over n ln n. Because you have a square root here on the denominator, this denominator is always going to be smaller than that one. Denominator is smaller means the entire thing is larger. So we're going to use the comparison test to say if this diverges, this must also diverge because it's larger. So the reason I chose this function is that this is easily integrable. Because if you notice, you have ln n and its derivative, 1 over n, in the function. This is going to be an easy one by substitution. So if we graph our integral, it's here from 2 to infinity, although in this case that really doesn't matter. We're going to have the function 1 over x ln x dx. So remember, this is all testing what's going on at 4, because we need to know if we need to change that to a bracket or leave it as a parentheses. So here we have 1 over x ln x. Excuse me. So when we take the integral of this, we're going to say u equals ln x for substitution. Therefore, du equals 1 over x dx. You can see that 1 over x dx is in the function. So after doing substitution, this just becomes 1 over u du. The antiderivative of 1 over u is simply ln u. So we're evaluating that from 2 to infinity, but we have to plug back in for u before you do that. So actually, let me erase that here. So you get ln u, which is ln of x, and we're doing that from 2 to infinity. Well, you can see here, or if you like, it's 2 to t, limit as t goes to infinity, but it's implicit here that we're doing the limit when we talk about the infinity. The limit as x goes to infinity of ln x is infinity, and then the same thing applies for that. So the top bound here gives you a positive infinity. When you plug in 2, ln 2 is some number, and when you do ln of that, you get another number. It's a constant, which when you're talking about dealing with infinities, that doesn't really matter. We get infinity, meaning that by the integral test, this function diverges. That means since this diverges and this is greater than it, this definitely diverges. So we have that this series right here, which was what we got out of our function if x was 4, diverges. So we know that this should be a parentheses there. Our series 4 is not in our interval of convergence. So now we need to check 3. So this is if x equals 4, Now we're just doing if x equals 3. So we're going to see if 3 is in our interval of convergence. So if we plug in 3 for x, it's almost the exact same thing. It's the same series we had here, except now it's alternating because we get -1 to the n in the numerator. So we get n equals 2 to infinity, -1 to the n over n square root ln n. This one is a bit simpler than our previous ones because this is an alternating series and we can just use the alternating series test. So by alternating series, remember all you need to show is that the limit as n goes to infinity of your series function is 0 and that every subsequent term is smaller than the one before it. So here we get, let's check our b sub n, which is the part of this series that doesn't have the alternating part. B sub n plus 1 needs to be less than or equal to b sub n for all terms. You can see here, if you increase n to n plus 1, you're only making the denominator bigger. Every n plus 1th term is going to be less than the nth term, so that's definitely true. We need to see the limit as n goes to infinity of b sub n equals 0. Let's see if that's true, and if both of these are true, then we can say this converges by alternating series test. As we go from n to infinity, again remember b sub n is this series without the alternating part. We get a denominator of infinity, 1 over infinity, that's going to be 0. So both of these are true, which means this converges by alternating series test. That means that x equals 3 is actually in our interval of convergence, so that needs to be a bracket. So our interval of convergence for this function is from 3 to 4, including 3 and excluding 4.
The Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.